Coming back from the moon is harder than going there. A spacecraft can travel hundreds of thousands of miles through space, loop around the moon, and return to Earth. From a distance, it looks simple. But during the Artemis II mission, that return involved losing communication, entering the atmosphere at extreme speed, and surviving temperatures hot enough to melt metal. So why does a moon mission look simple but isn't? To answer that question, let's follow the journey, not as a timeline, but as a system. At first glance, a moon mission seems straightforward. Launch from Earth, travel to the moon, and come back. But space doesn't have straight paths. Everything is already moving. The Earth is rotating. The moon is orbiting Earth. And your spacecraft is entering this moving system. So you don't aim at the moon. You launch at a precise moment, so your path naturally intersects where the moon will be. So far, this already breaks the illusion of simplicity. But the next step is even more counterintuitive. The spacecraft doesn't stop at the moon. It doesn't land. It doesn't stay in orbit. Instead, it performs a lunar flyby, passing around the far side of the moon. This is not just a pass. It's a turning point. The moon's gravity bends the spacecraft's path and sends it back toward Earth. But something else happens here. As the spacecraft moves behind the moon, Earth disappears from view, and with it, communication. For about 40 minutes, there is complete silence. Even when communication is active, there's still a delay. Signals between Earth and the spacecraft take about a second to travel each way. You're not in real-time control. You're operating within a system that has already been set in motion. So far we've seen, you can't launch anytime, you don't travel in a straight line, you don't stay in constant contact. But this still doesn't explain the hardest part, coming back. After the lunar flyby, the spacecraft doesn't rely on engines to return. Instead, it follows a free return trajectory. Gravity does the work. Earth pulls it outward. The moon bends its path, and Earth pulls it back in. So far, this might feel elegant, even simple. But this still doesn't explain the real challenge. By the time the spacecraft returns to Earth, it is traveling at nearly 40,000 kilometers per hour. Now here's the key idea. Speed is not just motion. It is stored energy. Think of dropping a ball. From a small height, it lands gently. From a great height, it hits much harder. The spacecraft is doing the same thing, but from the distance of the moon. Now here's where everything changes. As the spacecraft enters Earth's atmosphere, it doesn't gently slow down. It collides with air at extreme speed. But the heat is not caused by simple friction. Instead, the air in front of the spacecraft gets compressed. Compressed gas heats up rapidly. So rapidly that temperatures reach around 2700 degrees Celsius. The air turns into plasma, a glowing layer surrounding the spacecraft. That's why it appears as a fireball. Now here's something even more precise. The spacecraft must enter the atmosphere at exactly the right angle. Too shallow, and it skips off into space. Too steep, and it burns up. This safe region is called the reentry corridor, and it is extremely narrow. As plasma forms around the spacecraft, it blocks radio signals. This creates another blackout. No communication, no external guidance, only onboard systems and physics. So far, we've seen something important. A moon mission is not a powered journey. It is a carefully balanced interaction between gravity and energy. This reveals something deeper about space travel. Space itself is predictable. There's no air, almost no resistance, only motion shaped by gravity. That's why most of the journey feels controlled. But Earth changes everything. The same atmosphere that protects life becomes the hardest part of returning, and the communication delays reveal something else. Even at the moon's distance, you are not in constant control. You are operating within physics, not overriding it. And this is what Artemis II was testing. Not just whether we can go to the moon, but whether we understand the system well enough to come back safely. The next mission, Artemis III, is expected later this decade. Its goal is different. Not just to fly around the moon, but to work near it and return humans to its surface. And that depends on something fundamental: confidence in a system proven by Artemis II. If you enjoy understanding the why behind things like this, you'll find more like this on the channel. So what is really happening in a moon mission? It looks simple, but it is built on layers of hidden complexity. You don't fly straight to the moon. You align with it. You don't power your way back. You let gravity guide you. And you don't gently return to Earth. You release enormous energy as you pass through the atmosphere. What appears to be a smooth journey is actually a precise interaction between motion, gravity, and energy. And the reason it feels simple is because all that complexity is hidden behind a perfectly designed path.